Most important questions of magnetic effects of electric current. Class 10 Science. Question. What is meant by magnetic field? Answer. Magnetic field. It is defined as the space surrounding the magnet in which magnetic force can be experienced. Question. Draw magnetic field lines around a bar magnet. Name the device which is used to draw magnetic field lines. Answer. Answer. Compass needle is used to draw magnetic field lines. Question. A. Mention two parameters that are necessary to describe magnetic field completely. B. If field lines of a magnetic field are crossed at a point, what does it indicate? Answer. A. Necessary parameters are times magnitude of magnetic field times direction of field lines. B. If field lines of a magnetic field are crossed at a point, it indicates that there are two directions of magnetic field at a point which is not possible. Question. A compass needle is placed near a current-carrying straight conductor. State your observation for the following cases and give reasons for the same in each case. A. Magnitude of electric current is increased. B. The compass needle is displaced away from the conductor. Answer. A. As the amount of magnetic field strength is directly proportional to the amount of current, so the deflection of compass needle increases. B. Since magnetic field strength at a point is inversely proportional to the distance from the wire. Hence, deflection of compass decreases when it is displaced away from the conductor. Question. State how the magnetic field produced by a straight current-carrying conductor at a point depends on A. Current through the conductor, B. Distance of point from conductor. Answer. Strength of magnetic field produced by a straight current-carrying wire at a given point is A. Directly proportional to the current passing through it. B. Inversely proportional to the distance of that point from the wire. Question. Give reason for the following. I. There is either a convergence or a divergence of magnetic field lines near the ends of a current-carrying straight solenoid. 2. The current-carrying solenoid when suspended freely rests along a particular direction. Answer. I. There is either a convergence or a divergence of magnetic field lines near the ends of a current-carrying straight solenoid because it behaves similar to that of a bar magnet and has a magnetic field line pattern similar to that of a bar magnet. Thus the ends of the straight solenoid behaves like poles of the magnet, where the converging end is the south pole and the diverging end is the north pole. 2. The current-carrying solenoid behaves similar to that of a bar magnet and when freely suspended aligns itself in the north-south direction. Question. Find the direction of magnetic field due to a current-carrying circular coil held I. vertically in north-south plane and an observer looking it from east sees the current to flow in anticlockwise direction. 2. Vertically in east-west plane and an observer looking it from south sees the current to flow in anticlockwise direction. 3. Horizontally and an observer looking at it from below sees current to flow in clockwise direction. Answer. According to right-hand rule, the direction of magnetic field is I. West to east, 2. North to south, 3. Into the paper. Question. A. State 3 factors on which the strength of magnetic field produced by a current-carrying solenoid depends. B. Draw circuit diagram of a solenoid to prepare an electromagnet. Answer A. Strength of magnetic field produced by a current-carrying solenoid depends upon the following factors. Times number of turns in the coil. Times amount of current flowing through it. Times radius of coil. Times material of core of the solenoid. B. A strong magnetic field produced inside a solenoid can be used to magnetize a piece of magnetic material, like soft iron, when placed inside the coil. The magnet so formed is called an electromagnet. Question. A. State right-hand thumb rule to find the direction of the magnetic field around a current-carrying straight conductor. B. How will the magnetic field be affected on I. Increasing the current through the conductor, 2. Reversing the direction of flow of current in the conductor? Answer A. It states that you are holding a current-carrying straight conductor in your right hand such that the thumb points towards the direction of current. Then your finger will wrap around the conductor in the direction of the field lines of the magnetic field. B. I. If the current is increased, the magnetic field strength also increases. 2. If the direction of current is reversed, the direction of magnetic field also get reversed. Question. Diagram shows the lengthwise section of a current-carrying solenoid. Indicates current entering into the page, indicates current emerging out of the page. Decide which end of the solenoid A or B will behave as north pole. Give reason for your answer. Also draw field lines inside the solenoid. Answer. Using right-hand thumb rule, we can draw the magnetic field lines around the conductor as shown. From figure, end A of solenoid act as north pole and end B will act as south pole. Inside the solenoid field lines are in the form of parallel straight lines. Question. Write one application of right-hand thumb rule. Answer. It is used to find the direction of magnetic field around a current-carrying conductor. Question. A. State the purpose of soft iron core used in making an electromagnet. B. List two ways of increasing the strength of an electromagnet if the material of the electromagnet is fixed. Answer. A. The soft iron core placed in an electromagnet increases the strength of the magnetic field produced, thus increasing the strength of electromagnet. B. The strength of electromagnet can be increased by I. Increasing the current passing through the coil. 2. Increasing the number of turns in the coil. Question. What is solenoid? Draw the pattern of magnetic field lines of I. A current-carrying solenoid and 2. A bar magnet. List two distinguishing features between the two fields. Answer. I. Solenoid. A coil of many circular turns of insulated copper wire wrapped in the shape of cylinder is called solenoid. The pattern of magnetic field lines inside the solenoid indicates that the magnetic field is the same at all points inside the solenoid. That is, the field is uniform inside the solenoid. 2. Magnetic field lines around a bar magnet. Magnet. Following are the distinguishing features between the two fields. A. A bar magnet. Magnet is a permanent magnet whereas solenoid is an electromagnet. Therefore, field produced by solenoid is temporary and stay till current flows through it. B. Magnetic field produced by solenoid is more stronger than magnetic field of a bar magnet. Question. What are magnetic field lines? List 3 characteristics of these lines. Describe in brief an activity to study the magnetic field lines due to a current carrying circular oil. Answer. Magnetic field lines. These are the imaginary closed curves which are used to represent the magnetic field around the magnet. The properties of the magnetic field lines are listed below. Times magnetic field lines start at the North Pole and end at the South Pole. Times magnetic field lines do not intersect each other because there can't be two directions of the magnetic field at any one point. Times the degree of closeness of the field lines depends upon the strength of the magnetic field. Stronger the field, closer are the field lines. In order to find the magnetic field due to a coil, it is held in a vertical plane and is made to pass through a smooth cardboard in such a way that the center, O, of the coil lies at the cardboard. A current is passed through the coil and iron filings are sprinkled on the cardboard. These iron filings arrange themselves in a pattern similar to one shown in the figure. This pattern represents the magnetic field lines due to the coil. In order to find the direction of magnetic field lines, we plot the magnetic field with the help of a compass needle. The pattern of magnetic field lines so obtained is shown in figure B. B. From this pattern, the following important conclusion have been drawn. Times the magnetic field lines near the coil are nearly circular and concentric. This is due to the reason that the segments of the coil in contact with the board at the points A and B are almost like straight conductors. The direction of the field lines can also be found by applying right-hand thumb rule. Times the field lines are in the same direction in the space enclosed by the coil. Times near the center of the coil, the field lines are nearly straight and parallel. As such, the magnetic field at the center of the coil can be taken to be uniform. Times the direction of the magnetic field at the center is perpendicular to the plane of the coil. Times as we move towards the center of the coil, the strength of magnetic field increases. Magnetic field is maximum at its center. This is due to the reason that the two magnetic field, one due to the semicircular segment of the coil through A and the other due to the semicircular segment through B, assist each other. The magnitude of the magnetic field at the center of the coil is directly proportional to the current flowing through it and total number of turns and inversely proportional to the radius of the coil. This is due to the reason that the current in all the circular turns of the coil is in the same direction. As such, the resultant magnetic field due to the coil is equal to the sum of the field due to all these turns. Question. Draw the magnetic field lines through and around a single loop of wire carrying electric current. Answer. Question. State the effect of a magnetic field on the path of a moving charged particle. Answer. A charged particle moving in a magnetic field may experience a force in the direction perpendicular to direction of magnetic field and direction of motion of particle. This force deflects the charged particle from its path. Question. State the direction of magnetic field in the following case. Answer. Using Fleming's left-hand rule, the direction of magnetic field is out of the plane of paper. Question. Write one application of Fleming's left-hand rule. Answer. Fleming's left-hand rule is used to find the direction of force on a current-carrying conductor placed in a magnetic field acting perpendicular to the direction of current. Question. A current-carrying conductor is placed in a magnetic field. Now answer the following. I. List the factors on which the magnitude of force experienced by conductor depends. 2. When is the magnitude of this force maximum? 3. State the rule which helps in finding the direction of motion of conductor. 4. If initially this force was acting from right to left, how will the direction of force change if A. Direction of magnetic field is reversed? B. Direction of current is reversed. Answer. I. When a current-carrying wire is placed in a magnetic field, it experiences a magnetic force that depends on A. Current flowing in the conductor, B. Strength of magnetic field, C. Length of the conductor, D. Angle between the element of length and the magnetic field. 2. Force experienced by a current-carrying conductor placed in a magnetic field is largest when the direction of current is perpendicular to the direction of magnetic field. 3. The rule used in finding the direction of motion of the conductor placed in a magnetic field is Fleming's left-hand rule. Fleming's left-hand rule is as follows. Stretch out the thumb, the forefinger, and the second middle finger of the left hand so that these are at right angles to each other. If the forefinger gives the direction of the magnetic field, N to S, the second middle finger the direction of current, then the thumb gives the direction of the force acting on the conductor.